Hello everyone. Today we will study about oscillators and 555 timers. Last class we studied about RC phase shift oscillator. So today we will be studying about Wien bridge oscillator. Later we will be studying about 555 timers and its variation. Coming to Wien bridge oscillator, it is so called because the circuit is based on a frequency selective form of the Wien bridge circuit. So it is called because it is a circuit based on the frequency selective form of the Wien bridge circuit. There is a small circuit here in the below. The Wien bridge oscillator is of two-stage RC coupled amplifier which has a good stability and its resonant frequency. So low distortion and it is very easy to tune, making it so popular for your audio frequency oscillators. So whenever I speak about Wien bridge oscillators, it's a RC coupled amplifier circuit. It's called a two-stage, and it is a good stability. Because of this good stability and low distortion, it is used in audio frequency oscillators. But the only thing is, it has a phase shift of output signal. It is considerably different in your previous phase shift RC oscillators. So let me explain. This Wien bridge is called a circuit which is based on a frequency selective form, and we see here it uses a feedback circuit, consists of a series RC circuit connected in a parallel RC of the same components. One will be the series combination, one will be the parallel combination. So all your resistances are same. That's R1, R2 is same, C1, C2 is same. So R1 and C1 are series and R2, C2 are series. So if you observe the circuit below, so one is your high pass filter, the other one is low pass filter. Coming to the circuit, the network consists of a series RC circuit connected to a parallel RC form. Basically, it is called a high pass filter connected to a low pass filter, producing a very selective second order frequency. So what happens at low frequency and high frequency? See, at low frequencies, the reactance of series capacitor is very high. So it acts as a bit like an open circuit. So what happens here? At low frequencies, the reactance of a series capacitance. I am speaking about a series capacitance. What happens in a series capacitance? It has very high reactance, so it will work as an open circuit. It works as an open circuit, blocking any input signal at Vin, resulting in no output. So your output will be equal to 0. So your output will be equal to 0. So what it says here, a low frequency, the reactance of the series capacitor. For a low frequency, the reactance of series capacitor, will be high. It will be high. What will be high? The reactance will be high. If the reactance is high, the circuit becomes open. So if the circuit is open, so from V in to V out will be equal to 0. Likewise, we will see high frequencies. In higher frequencies, the reactance of parallel circuit. So I am speaking about parallel circuits. In a parallel capacitor, the reactance becomes very low or becomes very low. It's like a resistance. Reactance becomes very low. When reactance becomes very low, it becomes a closed circuit. When it becomes a closed circuit, if you see here, when it becomes a closed circuit, it is a short of your output. So output obviously becomes 0. When a capacitor is in series for a low frequency, it becomes an open circuit. So when it becomes open circuit, why it becomes open circuit? Because of high reactance. Because of high reactance, the circuit becomes open. It becomes an open circuit. So output will be equal to 0. Same way, when a capacitor is connected in parallel, because of high reactance, what happens here? What happens? It becomes a closed circuit. It becomes a closed circuit. It becomes a short circuit of your output. So your output becomes again 0. Understood? Probably I am telling in a different way. Try to understand this. For low frequency, your reactance will be high. So your circuit becomes open. Simple. These two steps you remember. One step is for low frequency, the reactance will be high. The capacitor becomes open circuit. Then your output is 0. Second part. For high frequency, the reactance becomes less. So it becomes closed circuit. It becomes closed circuit, output is 0 because output is shorted. So these are the two things you need to remember for a low frequency and for high frequency. Low frequency, for a low frequency, the reactance increases, the circuit switch becomes open, output is 0. For high frequency, reactance is low, but the output becomes short and output is 0. So these are two things you need to remember. So there should be a frequency point between these two extremes of C1 being open circuited and C2 being short circuited. So C2 becomes short circuited where the output voltage Vout reaches its maximum value. So what happens here? There must be a frequency point where there are two extremes, when C1 being open circuited and C2 being short circuited, where the output voltage Vout reaches to its maximum value. That we need to see. The frequency value of the input wave here, at which it happens, it's called oscillator resonance frequency. That's called FR. That's called FR frequency. So at resonance, what happens? You have to see. At the resonance frequency, the circuit reactance equals its resistance. So what do you mean by that? So let us see here. What happens at the resonance? At the resonance, the circuit reactance equals its resistance. That is, Xc will be equal to R. This is reactance and this is resistance, circuit resistance. And this two becomes equal. The phase difference between the input and output equals 0 degree. What happens then? The phase difference between the input and output phase becomes 0 degree. And coming to the magnitude of the output voltage is therefore at its maximum. So what happens? The magnitude of the output voltage therefore at its maximum will be equal to 1/3 of the input voltage. So your output will be equal to 1/3 of your input. So the magnitude of the output voltage is therefore at its maximum and is equal to 1/3 of the input voltage as shown in the circuit here. So that is about high pass, low pass and resonant frequencies of the system. Okay, we'll start with the next one. Coming to the graph, it has been seen that a very low frequency, the phase angle between the input and output signal is positive. The input and output signal is positive. Phase advance we call it as. While at a very high frequency, the phase angle becomes negative. You can see here. We can see here becomes negative. Low frequencies, the phase angle between the input and output signal is positive. This is positive. So as the higher frequencies increases, the phase angle becomes negative. That's called phase delay. So in middle of these 2 points, if you observe, so there is a middle of these 2 points. This point, this one, this part. The circuit is at its resonance. This part is called resonance. That part is called, this one is called resonance or resonance frequency, FR, resonance frequency, which is a two signal being in phase, or we call it as 0 degree. We can therefore define this resonance frequency point with the following expressions. We will see what is that frequency, that is FR is equal to 1 divided by 2 pi R into C. What is this? FR is the resonant frequency, that is always in hertz, frequency in hertz. R is in resistance in ohms and C is in capacitance. So come back to again the same thing. So when you see here, for a low input frequencies, for a positive, the signal is positive. The signal is positive. And for high frequencies, the phase angle becomes changed and goes to negative. That's called phase delay. This is called phase advance and is called phase delay. And this middle point you are observing here, what is at 0 degree, that is called resonant frequency, where the two signals being in phase. So that is called 0 degree. And this is derived from FR is equal to 1 divided by 2 pi RC. Okay. Okay. Go to the next one. So next topic is on 555 timers. So let us see how the 555 timers works. So coming to the 555 timer. So this is 555 timer. IC time, it is of 8 pins. Pin number 1, pin number 2, 3, 4, 5, 6, 7 and 8. Usually pin number 8 and 4 will be connected to positive VCC plus VCC. And your pin number 3 will be your output. And pin number 2 is called trigger, 6 is threshold and 7 is discharge. 5 and 1 usually will be connected to ground. 5 with a capacitor, a small capacitor, and 1 will be connected to ground. This is the general way of connecting a 555 timer. So internal structure, if you observe here, pin number 1 is connected to a transistor emitter, and pin number 7 is connected to a collector here. And threshold, if you see it, there is a 2 op amps with a flip-flop, as works as a sub flip-flop, and its output is driven to a pin number 3. So there is a trigger pin which is connected to one of the op amp, and the output of one op amp, that is nothing but it's a reset from a flip-flop. This is the internal structure of your 555 timer. Just remember the few points. So it starts from pin number 1 to pin number 8. So totally, if you take an IC with a notch, it starts from 1, 2, 3, 4, 5, 6, 7 and 8. 8 will be here. This is 5, this is 4 and this is 1. So this is 555 IC. It's a small IC. So pin number 1 is ground. The ground pin connected to 555 IC to the negative of supply voltage. That is nothing but 0. So if you observe here pin number 2, it is a negative input to the comparator. Pin number 2, which is a negative input to the comparator here. Negative input to the comparator 1. So there are how many comparators? 2 comparators. Comparator 1 and comparator 2. A negative pulse on this pin sets the internal flip-flop. When the voltage drops below 1/3, that is important. That voltage drops below 1/3 VCC, causing the output switch from low to high. So your output becomes low to high. So that is the trigger pulse. So trigger pulse is a negative pulse. So when it will be causes your output from low to high, when it causes your output from low to high, when the input is falls below 1/3 of VCC. So that is the trigger pulse of your 555. Coming to output, the output can drive any TTL. TTL means transistor logic. It can drive any transistor logic loads, which is capable of sourcing or sinking. So what is sourcing and sinking? Source and sink. So I'll see that how your source and sink will work. Let me go back. Okay, this is my IC. This is pin number 3. Source means I'm connecting one LED here with a resistor to the ground. This is called sourcing. With a LED. Okay, wait, let me tell you one more method of clearing this. Let me use a different color, that will be better. One minute. So this is called source. So what is 3? 3, I'm getting an output. I'm connecting one LED with a current limiting resistor. So when I give a pulse, my output becomes, if my output becomes high, the LED will be in on condition. This is called sourcing. So it is providing a pulse to this as a source, that is higher potential, and this is at lower potential. This is at higher potential and this is at lower potential. This is called sourcing. So this is working as a source. Higher voltages plus 5 volts is the source. This is called sourcing. When the load is connected to ground and the supply I am getting it from pin number 3 means it is called sourcing. Then what is sinking? Sinking is opposite to this. So let me draw the diagram here. This is pin number 3. So I have to do it in a reverse order. Let me take this in a different way with a resistor and connecting that to plus 5 volts. Now you understood, I think. Here it is sink. Now what happens? The voltage already I have given 5 volts, but until your output becomes low, your LED will not be on. So when it becomes 0, your pin number 3 becomes 0, your LED will be in on condition. When your pin number 3 becomes 0, your LED will be in on condition. When your pin number 3 is equal to 1, LED will be in off condition. So that is the difference between source and sink. In source 3 is an output, so it gives 1, the LED will be on. When it gives 0, LED will be in off condition. But here it is opposite. When 3 gives 0, your output will be, your LED will be on. Your 3 output is 1 means LED will be off, just like your NOT gate. That is source and sink. Let me write the same truth table here. 1 and 0. For 1, your LED will be in on condition. For 0, your LED will be in off condition. That is called source and sink. In source, if the 3 output of 3 is high, then your LED is on. If output of 3 is 0, that is ground, LED is off. But in sink, see the circuit combination, it is opposite. In sink, if the output of 3 is ground, the LED will be on. The output of 3 is 1, that is high, 5 volts, then your LED will be in off condition. That is called source and sink of your pin number 3. Okay, coming to pin number 4, that is nothing but a reset. Pin number 4. Pin number 4, it's called a reset. So in a reset, the internal flip-flop controlling the state of the output. You can see here, pin number 4, in a flip-flop, this pin is used to reset the internal flip-flop controlling the state of the output of your pin number 3. This is always active low input and is generally connected to logic 1. That is the reason the previous I said 8 and 4 will be connected to plus VCC. When it is not been used to prevent any unwanted triggering, your 4 will be always connected to plus VCC. Try to understand. This pin is used as a reset for an internal flip-flop controlling the state of your output pin number 3. This is active low input and is generally connected to pin number 4, which is to high, or we call it as 1. So that is pin number 4. So coming to pin number 5, so it is called control voltage. Coming to control voltage, this pin controls the timing of your table 5 by overriding the 2/3 of VCC. Previously we studied about 1/3 of VCC. Here we speak about 2/3 of VCC, level of your voltage divider network. So your timing is controlled by this control voltage. If the voltage is 2/3 of VCC, there is a trigger. By upping the voltage to this pin, the width of the output signal at pin number 3 can be varied independently with respect to R and C timing network. If you are not used, you can directly connect this pin to one capacitor to the ground to eliminate the noise. That is called 10 nanofarad capacitor. I repeat once again. So why we use this pin number 5 is to vary the width of the pulse of your output irrespective of R and C combinations in your circuit. We'll come back to this, how your R and C circuit are connected to your 555. So there you will understand. Without R and C what happens, with an R and C what happens. So with R and C, if I want to change the output of the waveform, if I want a 50 to 50 duty cycle, and in some time I need a 50% duty cycle and 70% duty cycle, again 50%, again 70%. To have this, I don't want to change this R and C. I just need to change the voltage of 2/3 of VCC. That is by control voltage. That is the reason we use pin number 5. So with the combination of R and C, if I want to have a varied output waveform, then I need to use this control voltage of pin number 5. Or else, if I don't want this option, then I can directly connect this to ground using a 10 nanofarad capacitor. That is what happens in your 555 of your pin number 5. Okay, next pin number 6. It's called threshold. The positive input to the comparator of pin number of comparator 2. It's a positive. You can see it now, it's not connected to negative, it is connected to positive pin. This pin is used to reset the flip-flop when the voltage applied to it exceeds 2/3. So why we use this? If the voltage exceeds 2/3 of VCC, I'm going to reset my flip-flop, causing the output from high to low. So if I want to have a pulse, I want a pulse on, off, on, off, on, and off. So for on, my 2/3 of VCC should be greater than 2/3 of VCC in a control voltage. And since sometime if I use a threshold voltage here, if it exceeds 2/3 of VCC, then your output becomes high to low. So that is the reason you will get on, off condition continuously. Stable output. So there we use this threshold. So I'll repeat it once again. This pin is used to reset the flip-flop. That is the second flip-flop. And when this will be resetted? When it exceeds 2/3 of VCC, causing the output to switch from high to low. So this pin is directly connected to your RC circuit. RC circuit is nothing but a resistor and a capacitor combinations. At this point, we are going to connect to your pin number 6. So this we will be studying in the next coming slides. So why we use threshold pin 6 and where we use it. Okay, that is your pin number 6. Coming to pin number 7, it's called discharge. The discharge pin is directly connected to where, as you can see, the collector of an internal NPN transistor. It is used to discharge the timing capacitor to ground when the output switches over to 0. So what happens? I need on, again I need off. So I need off, I need on. So one minute. One should be 1, then it should be 0, then it should be 1, and then it should be 0. So because we are using a RC constant combination, so once when I charge the capacitor, the output goes to high. When the capacitor starts discharging by using pin number 7, then your output should go to 0. So this combination I'll show you how we are exactly connecting your pin number 6 and pin number 7. And just randomly telling you in between, but it may be here or it may be here. I'll tell you later. So just try to understand when the capacitor is getting charged, your output will rise and becomes high. When your capacitor starts discharging, your output becomes low and it will be low until again the cycle repeats, again charging, again discharging. So this is controlled by your threshold and discharge as well as control voltage. So if you are using RNC combination without your pin number 5, then only 6 and 7 is needed for a continuous pulse. So that is the working of your pin number 7. And coming to pin number 8. Pin number 8, we all know it's a power supply to the system. And generally we can call it as general purpose TL table 5 timer, which works at 4.5 volts to 15 volts. It works at this voltage. So this is about your table 5 timer. So we will be studying about this in depth, how to connect the RC constant values and how to generate a signal, how your monostable multi-evaporator will work, how your bistable will work, what is a stable, where do you use that, what are the applications of it, and how we can come across the advantages of using this table 5 timers. Hope you all understand which are the pins and what are its functions. Pin number 1, pin number 2, 3, 4, 5. So most of the time your output waveform is controlled by your 6th pin and 7th pin. So with RNC, if I want to vary my output waveform, then we use pin number 5. In 90% of the circuits, we use pin number 5 with a capacitor to the ground. It may be 3.3 nanofarad or 10 nanofarad. Hope you understood these concepts. Okay. So we will continue with the class with the next session with the circuit diagrams. Okay. Thank you all.